Swayam Prabha. Digital India. Educated India.
Yeah, so we will start with pipelining. So let us look at this particular diagram. There are two parts to this circuit. So the inputs come from this point. It gets processed by part 1 and then it is fed to part 2. It gets processed and it comes out. So let us assume that part 1 takes 10 milliseconds of time and part 2 takes 15 milliseconds of time. So when a data enters at this point, for it to come out of part 2 completely processed will take 25 milliseconds of time, sorry 25 milliseconds of time. And suppose I have 100 sets of data, for me to finish processing of this 100 sets of data would be 2500 milliseconds, right. So this is a circuit with part 1 10 milliseconds, part 2 15 milliseconds, total time is 25 milliseconds for processing one set of data. And then suppose we are processing 100 sets of data, it will take 2500 milliseconds, right. Now suppose I put a storage element in between, right. So what happens here, this storage element is nothing but a register and it gets powered by a clock. Now what happens is I can get the first set of data and it will get processed. So let us say there is a clock going like this. So the first set of data comes in, within one clock pulse, that is this duration, this data will get processed by part 1 and it will be available for storage in this part. So when the clock pulse comes, that is with this clock pulse come, the processed part of the first set of data essentially gets stored in this storage element. Okay. Please note that this is a flip flop. So what is a flip flop? The content of it will change only at the positive edge of the clock or negative edge of the clock. Let us assume it is positive edge. So what happens at this particular clock edge, the first set of data enters, it gets processed in part 1. At the end of this, when the next clock pulse comes, that processed result is stored here. Correct? Is it okay? And what will happen from this clock to this clock, as you see here, in the second period, this set of data gets processed by part 2 and in the next clock pulse it will be available as an output, right. So in clock k the data enters, in clock k plus 1 that intermediate results get stored in flip flop, in clock pulse k plus 2 the answer comes out, fine. Now please note that between k and k plus 1 part 1 was working, between k plus 1 and k plus 2 part 2 was working, between k and k plus 1 part 2 was idle, between k plus 1 and k plus 2 part 1 was idle. So what I can do is I will pump the first data. Now in the next clock pulse I can pump the second data here. So what will happen in the first clock pulse, D1 enters, D1 reaches here, at this point I can say D2 also enters the system, D2 enters here, and during the second clock pulse, that is between k plus 1 and k plus 2, what will happen, part 2 will be processing D1 while part 1 can be processing D2, right, and all that you are processing will not affect the input to D1 because this is a storage element and any change here will get into the storage only at the next rising edge. So essentially the storage element acts as an isolation between these two stages, okay. So D1 enters at clock k, So D1 enters at clock k, at clock k plus 1 D1's intermediate result is stored here. This is at clock k plus 1. At that clock k plus 1 D2 enters. Between k plus 1 and k plus 2 D1 is processed here while D2 is processed. In the clock k plus 2 D3 enters, D2's intermediate results are stored, and so between k plus 2 and k plus 3 D2 is processed and D3 is processed. So this is how the data can flow. Okay. So what happens now? We took 2500 milliseconds for processing 100 sets of data, 25 milliseconds per data. Now what will happen? This is 15 milliseconds, this is 10 milliseconds, right. So the first data will come when? Please, I have the same clock pulse. So the what should be the time period of the clock pulse should be at least 15 milliseconds, right, should be at least 15 milliseconds. If it is less than 15, then this fellow cannot finish. So it is, so the first set of data will come only at 30 milliseconds, and then after that every 15 millisecond you will get one data. So totally I will finish the entire operation by 1515 milliseconds. So 1000 data that took 2500 now can finish in 1515, which is at most 40% improvement, right, at least 40% we have improved. Is it okay, right? So this is the notion of pipelining, and what we do here in pipelining is that we introduce a storage between two parts of the circuit, and that storage will be like an isolation, so that one part can work on different set of data without influencing the next part which is working on some other set of data, and like this I can allow data to keep flowing. Are you able to follow? And one of the important things that you should note here is that the frequency of the clock, the time period of the clock is dictated by the part of the circuit that has maximum delay. So how do you improve on this? Now before going forward, please note that this is an example of what we call as functional parallelism. Why this is functional? Why this is called functional parallelism? Because I have different data sets, meaning the different instructions, right, and they are acted on by different part of the circuit, right. So different parts of the so each circuit can represent an instruction, right, that is working on the data. So I have different instructions acting on different data, right. Part 1 is working with, part 1 is an instruction, part 2 is another instruction. When part 1 is working on D1, part 2 will work on D2. When part 1 is working on D2, part 2 will work on D3 or whatever, vice versa. Okay. Now what happens because of this? I have multiple instructions. Part 1 is an instruction by itself, part 2 is an instruction by itself, and I have multiple data. So a pipeline is an example of a multiple instruction, multiple data environment. So any time you have a very large circuit in which we can do continuous operations like multiplication, I may not just have two numbers to be multiplied, I will have several pairs of numbers to be multiplied in a program. So if we get such type of a circuit where I could give continuous flow of data, then the best thing is to pipeline, and by pipelining already for a simple of the circuit, with a small pipelining introducing of a storage element, we could get up to store up to 40% saving in your time. The same thing is also possible. So this is actually useful in the context of using the same circuit for different sets of data, right. So I had one circuit which I pipelined, and then I am using it, for example multiplier is an example of a circuit you will be using for multiplying thousands and millions of numbers, right. And if you have such type of things where I could have continuous flow of data, then functional parallelism or whatever pipelining is extremely useful. Okay. Any doubts? Can I proceed? Okay. Now let us, I'll just do this simple thing of how to convert a circuit, a combinational circuit into a pipeline circuit. Okay. Any combinational circuit is basically a directed acyclic graph. What do you mean by a directed acyclic graph? It is a graph, it is a directed graph in the sense that every edge has a direction, right. For example, this is a directed acyclic graph. Okay. Probably I will have something here and then it goes like this. This is an example of a directed acyclic, where every edge has a direction. It goes from I to j, and there is no cycle. I can't start from any of this node and come back to that node. For example, I start with I1, and I can go to I2. No way can I come back to I1. So I can only go to I4, I can't come back to I5, I can go to I6 and finish. You are able to follow this? So no way can I come back to the same thing in a directed acyclic graph. That is why we call it as an acyclic graph. There is no cycle here, that is why we call it as an acyclic graph. So every node of this directed acyclic graph is a subcircuit of the given circuit. So I can have AND gate, OR gate, multiplier, etc. And I could have larger thing, I could have an adder, I could have all the standard cells here, and that could form a stage of a pipeline. So an edge of the DAG connects two nodes of the DAG. So what we do, we first do a topological sorting of the DAG. So let me just tell you what do you mean by topological sorting. This is the basic circuit which has 8 combinational elements. Each of these elements can be some adder, subtractor, or it can be a big combinational circuit. Now this is the thing, and now what happens, I do something called topological sorting. What is topological sorting? First I will remove all the primary inputs. When I remove all the primary inputs, I will now go and find out what are all the nodes that does not have any input node at all, input edge at all. So what are the nodes? N1, N2, N3. This I call it as level 0 or level 1, you see. Now I remove all these nodes and all the edges on these nodes. So essentially we remove off all these nodes. Now we find out who are all the fellows who does not have any input nodes. Then it becomes N4, N5, N6. I remove them, then it becomes N7, then finally it is N8. So this is basically topological sorting. So I will just do that sorting now as we see here. So first I remove all the primary inputs, these 3 nodes N1, N2, N3 became level 0. Next I remove N1, N2, N3, sorry, we call it level 1 here. And then we remove N1, N2, N3, so N4, N5, N6 comes up, and that is level 2. I remove N4, N5, N6, please note only N7 is removed because N7 has an edge to N8. So this becomes level 3, and then N8 comes in, so this becomes level 4. This is basically what we call as the topological sorting of any directed acyclic graph. What we do, we remove the primary inputs, we get all those shaved nodes N1, N2, N3. I remove, so that I make it as level 1. I remove N1, N2, N3, I get now these shaved nodes like N4, N5 and N6. Now I mark it as level 2. Then I remove N4, N5, N6. Now the only node left is N7, N8 cannot be inside. So N7 is level 3, and then N7 is removed, N8 becomes level 4. Are you getting this? So this is how I do a topological sorting of a given circuit. Now what we do to pipeline this circuit, we actually connect it with the edge so that between vertices, such that for every edge that is connecting between j and k, where j is some level, k is level, I will put k minus j storage levels in between. For example, n1 is in level, n1, n2, n3 are in level 1, n4, n5, n6 are in level 2, n7 and n8 are in level 3, n7 is in level 3, sorry, n7 is in level 3 and n8 is in level 4. Now between n1 and n4 there was an edge, there is an edge. Now how many storage I will put in between storage levels? Between n1 and n2 the difference is 2 minus 1, that is 1, so I put 1 storage. Between n3, n7 and n1 the difference is 2, so I put 2 storage, namely the red and the green. Are you able to follow? Between n1 and n7 it is 3 minus 1, 2, so I put 2 storages here, the red and green. Between n2 and n5 the difference is 1, because n5 is level 2 and n2 is level 1, then I put only 1 storage, and similarly n3 and n5 there is only 1 storage I put here. Now coming to n4 and n7 is at one level, so I put 1, n7 and n5 there is only 1, n1 and n7 it is greater than 1, so I put 1 here. Between n5 and n8 this is 4, sorry, this is 4 and this is 2, so 2 storages. Between n6 and n8 again 2 storages. Between n7 and n8 there is 1 storage. Right. So what I have done a topological sorting. For every vertex I have assigned the level, and if there is an edge connecting level k and level j, a level k node and a level j node, you essentially put k minus j storage elements in that edge. Okay, right? Are you able to follow? Once I do this, what will happen? Now the first set of data comes, it gets processed in the it gets processed at the first level and gets stored on the red as first data processed. It gets stored on the red. In the next cycle the second set of data comes to level 1, the first set of data is fed down to level 2 nodes. So this is feeding, this is feeding and this is feeding. At the end of the second thing, what will happen is your data will now go and stay in all the greens here, right. So the first set of data entered, in the first clock pulse it came to the red block, in the second clock pulse it moved to the third block, the green block, sometime through a node or sometimes just direct transfer from a buffer, as you see here. Now, so the first set of data it is in red. Now in the next clock pulse first will be in red, first will be moved to green after passing the level 2 processing or directly, and second will be in red. At the end of the third clock pulse, the first will be in blue, these entities, first will be in blue, second will be in green, third will be in red, correct. And at the fourth clock pulse the first will be in output, second will be in blue, third will be in green, fourth will be in red, and so on. Are you able to follow? Right. So I have introduced buffers in bit or storage elements between edges, right, and I have introduced that many storage elements, that is equal to the difference in the topological sorting. Once I put so many storage elements, please note that first set of data comes, it is executing and the result will be stored in the red. Now in the next clock pulse the second level nodes will start working on the red level nodes as their input, and they will start producing green level nodes. the green nodes. So the first set of data came to red and then to green. When the first set of data is in the green, the second set of data can be in the red. When the first set of data is in the blue, the second set of data can be in green, third set of data can be in red, and then we progress. Are you able to follow? Right. So please also note that there are cases where I will just be transferring information. I am not doing any processing between these two or these two here or these two. I am just forwarding the data so that I keep pace of the speed of execution, correct. So this is basically what I intend to teach you today. Now one of the important points you should have noticed is that let us go to this problem. If I had made part 1 as initially part 1 was 10 and part 2 was 15 and we got 1515 milliseconds, right. Now suppose I do some circuit level techniques and move some 2 millisecond worth of data outside this, then what will happen, part 1 will become now 12 milliseconds while part 2 will take 13 milliseconds. So what is the maximum time? 13. So when will the first data set finish? At 26 milliseconds, 13 for this, 13 for this, because I can't change the clock and all. And then after every 13 millisecond one data set will come. So essentially the total processing time for this 100 data set is 1313 millisecond. So we started off looking at 2500 milliseconds, from there we come to 2515, now it can be 1313 milliseconds. Okay. So this is got because I adjusted the storage so that they become almost equal, right. Once it was 10, another it was 15, I got 1515. Now I made one 12, another 13, they are almost equal. When the stages are almost equal, I get the maximum benefit. Is it okay? Are you able to follow? So when we do this pipelining, when we are doing this pipelining, please note that N1 to N8, right, are modules and they should have the same complexity in terms of time. One should not consume large delay, one should not consume. So essentially that means every stage is balanced. We call this word stage balancing. I need to balance the stage so that I get good speed up, and by not balancing the stage we landed up with 1515 milliseconds. Now with balancing the state we can lead up to 1313 milliseconds. Is it okay? Now let us talk about what is register transfer. So already we have seen in a pipeline circuit there is some register feeding a combination circuit which will again feed a register which will again feed a combination circuit. So the way we describe the design is how some set of data move from one register to another. That is why we call this as RTL, register transfer level. The entire modeling of this is done through RTL. So what would be the clock frequency here? It is 1 by 5 into 10 power 9, correct, because 5 nanosecond is 1 by 5 into 10 power minus 9 will be 1 by 5 into 10 power 9. That is the clock frequency, right. Suppose I go and make it as 4 nanoseconds here and 4 nanoseconds here and 4 nanoseconds here instead of 5 and 3, then certainly my frequency will become 1 by 4 into 10 power 9, that is 0.25, okay, into 10 power 9, right. So if I want to improve my frequency I need to balance my stages, okay. So that is what many of the carry ripple, carry lookup, Wallace tree multipliers, all of them when you take, you give a circuit, but what you do with the circuit is you go and pipeline the circuit so that we see that the frequency increases or your time period decreases. So when I make this 4 and 4, I use some circuit technique to make it 4 and 4. or I improve the technology so that 3 becomes 2 and this 5 becomes 4, automatically my frequency is going to increase, right. If my delay decreases, my frequency is going to increase, right. And that is also one of the reasons why laptops have lesser frequency ratings than desktop. Why? Because because these delays would be quite large in laptops. I will not give lot of power, so this cannot work very fast. Laptops are power hungry, so if I give less power, they will work slowly, and then that is why they are still slower. Then the clock frequency is slower, right. Okay, so this is what I wanted to cover today. So what we have done so far is we have learned what is pipelining, right, and there is a need for storage between two parts of the circuit to create isolation, and the data can be flowing from one end to another, and we model the entire operations as a register transfer level, wherein the data moves from one register to the next register and so on and so forth, right, in different clock pulse. So the way we describe the circuit, that itself is called register transfer level. So RTL description or RTL view, what it means, the data flows from one register stage to another register stage during the clock pulse. And then for me, the most important thing is I should have a balance in the pipeline. One stage should not be extremely slow, then the entire pipe will get completely screwed up. So we need to have that balance. We have given some examples of this. Ballast tree, so the example I gave here is very close to a ballast tree multiplier. So now given any combinational circuit, we can do a topological sorting, get the level numbers, then for every edge connecting I and j, the level number of j minus level number of I, that many storage elements we can put, and it automatically gives you a combinatorial arithmetic circuit which could be pipelined or which is already pipelined. So this is how we go and improve the speed. But pipelining is very, very important, is very, very useful when I have consistent flow of data. You getting this? If I don't have consistent flow of data, once in a blue moon I am going to do, then there is nothing that I will get here, right. But if I have consistent flow of data, one after another is coming for this, then pipelining becomes extremely effective. Now when we look at the benchmarks, right, traditional benchmarks that we have seen, there are a lot of benchmarks, almost all the benchmarks will have significantly large parts of the system which will allow you to do continuous instructions into the CPU or continuous set of data into the system, and then there these type of parallelization or this type of pipelining will be very, very useful. Okay, fair. So the most thing is that we need to get to equal. So what happens is when we design the circuits, when we design the circuits, we design it in some hardware description language, and we go and do a process called synthesis of this circuit. We do something called synthesis of this circuit. What is synthesis? You write something in a hardware description language like Verilog or whatever you did last time in your course, and that is converted into a gate level circuit. Right? Now when I convert it to a gate level circuit, there are tools, there are fabrication libraries basically come and tell us, so these are all the gates involved, these are the ways it is connected, it will give you what would be the delay. So I can estimate the delay while I am designing the system at a very early stage. The moment I have a description, I can give it to a tool, and the tool will convert it to gates, and then you will know that you are going to fabricate in some fabrication unit. That fabrication unit will tell you what are all the delays of the different components, and then you can estimate these delays. The moment I can estimate these delays, I can get a feel of the frequency, right. So very early in your design stage itself, you will get what would be the ultimate frequency. You will get a cap on what is the maximum frequency to which it can work. And if that does not suit your actual thing, then you probably start working at it at a very early stage to improve your frequency. Is it fine? So, this is something which is very interesting here. Okay. Thank you.